Welcome to my video abstract for my paper titled Combinatorial Watermarking under Limited SCR Adversarial Models. This paper is about the combinatorial watermark, which is where a fixed set of chips are inverted cryptographically in support of ranging authentication. The combinatorial watermark enables the computation of security statistic distributions, which is nice over other watermarks, and that allows you to compute and optimize probabilities of false alarm and misdetection. The security code and estimation replay adversarial model is been known for a while. And on screen, I have a diagram. On the left, you can see an adversary is listening to the satellite with the watermark chips. And inside the thought cloud, it's making a decision based off of its measurements. And then after that, it's broadcasting its spoof signal to a receiver. On the right is the BPSK constellation diagram. This is an example of an estimation that the adversary would have to do to figure out which chips are inverted. And you notice that there's a decision boundary alpha, and that can be set anywhere essentially. But you could try and optimize and say, well, there's a known prior probability of inverted chips if there's a fixed number of them. But in this paper, it's assumed that it can be any alpha. So on the left, we have the same decision, and it can be moved left or right. And as it moves left or right, the computed statistics of the security statistics will move as well. On the right, the green is the authentic distribution, and the red is the adversarial distribution. And depending on its decision moving left or right on the left, will determine where it is on that trajectory on the right. So the paper title includes limited SCR models. So one of the models talked about is called the hard decision SCR model. And with the hard decision, you can compute the expectation. And this shows a diagram of how the expectation trajectory changes as a function of the adversarial estimation SNR. So as the adversary has a better radio, it will better have the trajectory intersect the authentic distribution. I also talk about a soft decision model, which can do a little bit better. But with the soft decision, I know of no way to compute the distribution probabilities. So you can see on the screen I've simulated, and you can see a modest bump over the equivalent hard decision boundary because it's to the right of the line and closer to the authentic distribution.